piece of memory. Okay. So that would be all of the kind of very basic and like definition type stuff that I could ask. So we'll move on now to arrays as pointers. You should know the relationship between arrays and pointers. So this is really big. All arrays are actually pointers. And I know that, you know, like in CS1, when you learned like what arrays were, we didn't teach it like that. We didn't, you know, say it like that. But hopefully, you know, there are a few things that make a little bit more sense now that you know it, right? So like, for example, in CS1, whenever we said you're not allowed to just say like C out and your array name, right? When you're first learning about arrays, you feel like printing out the array name would go through and print out all the values, but it doesn't. It prints out an address of like where the values begin to be stored in memory. And that's really confusing. Like, why would it give me an address? Why doesn't it give me the values that's stored there? And it's because it's really a pointer. And that also explains why we use zero indexing, right? Because I'm saying go to this address, and then the number that we put inside the square brackets is your offset. How many spaces in memory, how many values in memory do I need to like go down to get to what I'm looking for? So if I want the initial value, I don't need to offset any at all. I don't need to travel anywhere. I'm already at where I want to be. So I would add 0 to that offset. Okay. So an array is just a pointer that stores the address of where the array starts in memory. So if I print it out like array, or if I print it out, like if I set a pointer that pointed to an array and I pointed the pointer out, printed the pointer out, tongue twister, they would be the same thing, right? Same thing. They're both addresses. Arrays are guaranteed to be stored in contiguous memory, and that means one right after another, okay? That's not always like with other data types. If I declared like 5 variables in a row, it would actually be unusual for them to be stored one right after another. That is most likely not what would happen. They could be stored anywhere where there's an opening. But if I say that I'm declaring an array, I am guaranteed that they're stored one right after another. And the reason that it has to be stored that way is because I start at that starting address, and then I can tell it, go down 2, go down 30, go down 12. And I know where I'm going to wind up. I know the value that's going to be stored there because they're all stored one right after another. So the notation, when I say like array name, like square bracket 2, I'm really saying go start at this address. That's my starting address. And then offset 2 address locations, move down 2 spots in there. That's exactly the same as saying go to this starting address and move down 2 places, move down 2 memory address locations. And then I say, this is your address. This is where I want you to go. Use that indirection operator. So get me the value that's stored there. That's how I access an element in an array. Okay. Because arrays store addresses, we don't have to use that address of operator when we assign them to a pointer. So that's kind of interesting. It already is an address. So this is valid. I don't need the ampersand. I can say the array has an address. I want an address directly stored in there. That's fine. That's assuming that array was an integer array, because the data type of this would need to match the data type of this. So, you know, I mentioned that parenthesis notation on the last slide, and you do need to be really careful with those parentheses. There is a difference between if I have parentheses around this or if I do not. So here I'm saying add 2 to the address and then use the indirection operator to get the value. But here I'm not saying that. I don't have parentheses. So I say get the value and then add 2 to it. So for example, if I had an array, and let's say the array was just the numbers like 0, 1, 2, 3, 4, 5. That's it. What is this saying? Start at 0, go to 1, go to 2, right? So those are my indices. Get the value that's stored there, 2. This is saying, get the value that is stored at this address. Well, okay, so this was a terrible example because they're going to wind up being the same thing. Let's say the numbers were 0, 10, 20, 30, 40, 50, or whatever, okay? We'll say 0 to 40. It's a 5-number array. So this would go get whatever's at index 2. So I could say like 0, 10, 20. This would return like the number 20. This would say, what is stored at the very beginning? Get that value, 0. Add 2 to it. 0 plus 2 equals 2. Right? So here I am adding to the address, and here I'm adding to the value. That's the difference between those two things. Okay. You can use that same addition notation that we're talking about here with pointers. You can use it with the array name too if you want to. That's totally valid because an array is a pointer. It's an address. This is the same thing as this. And basically, very smart people that were writing compilers like created this notation to make arrays a little bit easier to work with without having to do like the pointer notation. Just because pointers can be like confusing and they can be sort of error prone. And so this is just kind of like a nice little wrapper that says, I will let the programmer type it this way. And I, the computer, know in the background that what I'm really going to do is go to this address and add 1 and then get the values. You can still go out of bounds, just like you could go out of bounds using your square bracket notation. We need to be careful that we don't go out of bounds when we're using our addition notation. And C++ will let you overwrite values stored at those out of bound memory locations. And you don't know what's stored there. And it could have been something really important, like a part of your program that you needed to run. So you should be really careful with that. Okay, so I have an example. So in that code that I wrote earlier, so now we don't really need this other part. So I'll just remove it. And there is a hotkey to like block comment stuff out, but I'm typing with one hand here, so I won't worry about that. Okay. So here is another example. Here is another example. So this is dynamically allocating memory, right? I know that because I have the new keyword operator. So I created a pointer and I don't know where this points. This is just some random place in memory. And I didn't even give it a value. Like I have not initialized this pointer to hold anything. And what I have here is just a loop that's just going to run 25 times. And it says, tell me the address. And I can get an address with just the pointer name. And then I say, what is stored at that address? And this is all just going to be random. Like I have no idea what this is going to print out because you might have nothing stored in an address. You might have garbage stored in an address, or you might have like important like instructions and actual like pieces of the program. And because you don't know where things are stored, you don't know what's going to be at these particular locations. And this is just beginning at some like arbitrary starting point. So then I'm using some pointer addition here. I'm saying if I add 1 to the pointer, I'm adding 1 to the address. Okay, so what I'm saying here is go to the next address location. And here's another thing that's interesting. Because I said this was an integer pointer, it's going to move down memory locations 4 at a time. So whenever it prints out these addresses, we should see that they are increasing by 4 as we go. So I'll just run this. And you can kind of see what we get. So for the first few of these addresses, and yeah, see how I'm going like 0, 4, 8, 12, 0, 4, 8, 12. So we're going by 4s because we're adding 4 at a time because it's 4 bytes in an int for this particular environment that I'm in. So for a lot of these, they were just empty, right? A lot of them just had a value of nothing, but they don't all have a value of nothing. Here, there's just like some random numbers, all kinds of like just big, huge numbers, some small ones, some more that are empty. So you can kind of go through and see like what is stored inside the memory. It doesn't really tell you anything, but you can see that like that you could have stuff here that's empty and it would be fine to override it, but you can also have stuff here that could be important. And so you want to be careful of that. Okay. So what could I ask about the relationship between arrays and pointers? If I give you an array and a pointer that points to it, it would be fair for me to ask you to print out an element in the array using square bracket notation. That's the questions that y'all want because those are the CS1 questions. That's how you already know how to do it. But I could also ask you to print out an element in the array using the addition notation with that indirection operator. So what I mean by that is this. This is addition notation using the indirection operator. And if you remember, like I kind of had the notation right here, that notation is equivalent to this. This is the square bracket way of saying that same thing. Okay. I could ask you to know the difference in the order of operations with your parentheses. And I will ask questions kind of like this, where you need to know what's the difference between I'm changing the address or and then getting the value, or I'm getting the value and then doing some just basic arithmetic, like this is just a number. And so I can just add a number to a number. Okay. And then the examples that you could go back and look at to kind of make sure that you felt good about that or that you are well prepared for it is the questions will be similar to that worksheet we did when we first discussed pointers. It was the pointers predict the output. It came out of the textbook. There is, if you go into D2L in week 6, I have the handout and I have the answer key for it. And you can find that in your textbook if you wanted to kind of read some more about it.